When installing a transfer switch for a standby generator, the question of whether you need to run two neutral conductors from the service panel to the transfer switch and back arises. The National Electrical Code, or NEC, generally requires only one neutral conductor between the transfer switch and the service panel in typical residential applications. This is because the two ungrounded conductors, also known as hot wires or phase conductors, carry current in opposite directions. When these conductors are run in close proximity, such as within the same conduit, the magnetic fields tend to cancel each other out. This magnetic field cancellation effect minimizes the inductive reactance, which in turn reduces voltage drop and improves the overall efficiency of the electrical system. With balanced loads on a typical 120 volt/240 volt split-phase system, the current flowing through each ungrounded conductor should be approximately equal. Since the currents are equal and opposite, their magnetic fields effectively negate each other. This results in a minimal or near zero net current flowing in the neutral conductor. Because of this principle, a single neutral conductor is usually sufficient for carrying any imbalance in current between the two ungrounded conductors. However, there is an important exception to this rule, which involves nonlinear loads. Nonlinear loads are electronic devices and appliances that draw current in a non-sinusoidal manner. These types of loads can generate harmonic current, which are multiples of the fundamental frequency, typically 60 Hz in the United States. Common examples of nonlinear loads include computers, LED lighting, variable frequency drives, and some types of electronic ballasts. Harmonic currents do not cancel out in the neutral conductor like fundamental frequency currents do. Instead, they tend to add up, potentially leading to a significant neutral current. In scenarios where there are substantial nonlinear loads present, the neutral conductor may carry a current that exceeds its capacity, leading to overheating and potentially creating a fire hazard. To mitigate this risk, it is essential to evaluate the types and quantities of nonlinear loads present in the electrical system. If significant harmonic currents are anticipated, it may be necessary to run a second neutral conductor or to increase the size of the existing neutral conductor to accommodate the additional current. The NEC addresses this issue in section 250.30, which provides guidance on grounding and bonding requirements for separately derived systems such as those involving generators and transfer switches. This section emphasizes the importance of ensuring that the neutral conductor is adequately sized to carry the maximum neutral current that may be imposed upon it. To determine whether a second neutral conductor or an upsized neutral conductor is required, a load calculation should be performed taking into account the anticipated harmonic currents generated by nonlinear loads. There are specialized instruments available, such as harmonic analyzers, that can measure the actual harmonic content of the current flowing in the neutral conductor. This information can then be used to determine the appropriate size and number of neutral conductors needed to ensure safe and reliable operation of the electrical system. In addition to considering nonlinear loads, it is also important to ensure that the transfer switch itself is properly grounded and bonded. The grounding system provides a low impedance path for fault currents, helping to protect against electrical shock hazards. Bonding ensures that all metallic parts of the electrical system are electrically connected, minimizing voltage differences and reducing the risk of arcing or sparking. When installing a transfer switch, it is crucial to follow all applicable electrical codes and standards, including the NEC and local regulations. These codes provide detailed requirements for conductor sizing, overcurrent protection, grounding, and bonding. Consulting with a qualified electrician is highly recommended to ensure that the installation is performed safely and correctly. The electrician can assess the specific requirements of the electrical system, taking into account factors such as the size of the generator, the anticipated loads, and the presence of nonlinear loads. They can also ensure that the transfer switch is properly connected to the service panel and that all grounding and bonding connections are made correctly. In summary, while a single neutral conductor is generally sufficient for a transfer switch installation in a residential setting, it is essential to consider the potential impact of nonlinear loads and harmonic currents. If significant harmonic currents are anticipated, a second neutral conductor or an upsized neutral conductor may be necessary to ensure safe and reliable operation of the electrical system. Consulting with a qualified electrician and adhering to all applicable electrical codes and standards is crucial for a safe and code-compliant installation. Let's delve deeper into the NEC requirements, specifically focusing on Section 250.30, to understand the nuances of grounding and bonding separately derived systems. This section is particularly relevant when dealing with generators and transfer switches, as they effectively create a new source of power that must be properly grounded and bonded to ensure safety and prevent electrical hazards. Firstly, it's important to define what constitutes a separately derived system. According to the NEC, a separately derived system is an electrical source that is not electrically connected to the premises wiring. This means that the generator, when operating in standby mode, is providing power independently of the utility grid. As a result, it requires its own grounding and bonding system to ensure that fault currents can be safely conducted back to the source, tripping the overcurrent protection device and energizing the circuit. Section 250.30 addresses the grounding electrode system for separately derived systems. It mandates that the grounding electrode conductor must be connected to the grounded conductor, typically the neutral, of the separately derived system. This connection must be made at a single point, usually at the generator or transfer switch enclosure. The grounding electrode conductor then connects to the grounding electrode system, which can consist of various elements such as a ground rod, a metal water pipe, or a concrete encased electrode. The size of the grounding electrode conductor is determined by NEC Table 250.66 based on the size of the ungrounded conductors of the separately derived system. For example, if the ungrounded conductors are sized at 100 amps, the grounding electrode conductor would typically be no smaller than number 8 American wire gauge copper. Next, Section 250.30b addresses the bonding requirements for separately derived systems. Bonding is the process of connecting all non-current carrying metal parts of the electrical system together to create an electrically conductive path. This includes metal enclosures, conduits, and equipment grounding conductors. The purpose of bonding is to minimize voltage differences between these metal parts, reducing the risk of electric shock. The bonding jumper, which connects the equipment grounding conductors to the grounded conductor, must be sized according to NEC Table 250.102, based on the size of the ungrounded conductors. For a 100 amp system, the bonding jumper would typically be no smaller than number 8 American wire gauge copper. It's also crucial to ensure that all bonding connections are made with approved connectors and fittings, and that they are properly tightened to maintain a low impedance connection. One of the key considerations when installing a transfer switch is the type of transfer switch being used. There are two main types: manual transfer switches and automatic transfer switches. Manual transfer switches require the user to manually switch between the utility power and the generator power, while automatic transfer switches automatically switch to generator power when a power outage is detected. Automatic transfer switches offer greater convenience and faster response times, but they also require more complex wiring and control circuitry. Regardless of the type of transfer switch used, it's essential to follow the manufacturer's instructions and wiring diagrams carefully. These instructions will provide specific guidance on how to connect the transfer switch to the service panel, the generator, and the grounding system. It's also important to ensure that the transfer switch is properly rated for the size of the generator and the electrical load being served. Using an undersized transfer switch can lead to overheating and equipment failure. Now let's consider the impact of harmonics in more detail. Harmonic currents are generated by nonlinear loads, which draw current in a non-sinusoidal manner. These harmonic currents can cause a variety of problems in electrical systems, including overheating of neutral conductors, distortion of voltage waveforms, and increased energy losses. The most common harmonic currents are the odd-numbered harmonics, such as the third, fifth, and seventh harmonics. The third harmonic is particularly problematic because it is additive in the neutral conductor. This means that the third harmonic currents from all the single-phase loads on a 120-volt/240 volt system will combine in the neutral conductor, potentially exceeding its ampacity. To mitigate the effects of harmonic currents, several strategies can be employed. One approach is to use harmonic filters, which are designed to block or reduce the flow of harmonic currents. Harmonic filters can be installed at the individual loads that generate harmonics, or at the main service entrance to protect the entire electrical system. Another approach is to use transformers that are specifically designed to handle harmonic currents. These transformers typically have a larger neutral conductor and a higher K-factor rating, which indicates their ability to withstand harmonic heating. Additionally, it's important to select electrical equipment and appliances that are designed to minimize harmonic generation. Energy-efficient lighting, such as LED lighting, typically generates fewer harmonics than older technologies, such as fluorescent lighting with magnetic ballasts. In conclusion, when installing a transfer switch for a standby generator, it's crucial to carefully consider the grounding and bonding requirements outlined in NEC Section 250.30. A single neutral conductor is generally sufficient for residential applications, but the potential impact of nonlinear loads and harmonic currents must be taken into account. Consulting with a qualified electrician and adhering to all applicable electrical codes and standards is essential for a safe and code-compliant installation. Furthermore, continuous monitoring of the electrical system for harmonic distortion is recommended, especially in facilities with a high concentration of nonlinear loads. This can help to identify potential problems early on and prevent equipment damage or safety hazards. Remember, electrical safety is paramount, and proper grounding and bonding are critical for protecting people and property from electrical shock and fire hazards.